What's up, y'all? Just wanted to make this video quick about row echelon form and reduced row echelon form. So as you hopefully have realized, row echelon form is already a familiar term. We used it when we were solving systems of equations, and it's going to be very similar. And with matrices, it's just going to look a little different, just going to have a little different format. But for the most part, it can mean the same thing, and we can get more into how we can advance these processes as well. So we'll get into row echelon form quick. Matrix in row echelon form has three properties. Any rows consisting entirely of zeros occur at the bottom of the matrix. So in neither of these examples we have that, but if we were to have a row of zeros, it would be down here. So it would be 0, 0, 0, and that's the only place a row of zeros can go. Second, for each row that does not consist entirely of zeros, so any row with any values, the first non-zero entry is 1. It's called a leading one. So we see we have the first value here in this row is a 1, first value in this row is a 1, first value in this row is a 1. And then the third one, for two successive rows, the leading one in the higher row is farther to the left than the leading one in the lower row. So the leading one in the higher row is farther to the left than the leading one in the lower row. So we kind of got the stair pattern here. And this is how, or this represents how we would solve our systems of equations. We would try to get our z isolated first, or our z isolated first with whatever this number is, and then back substitute it to find y, and back substitute to find x. So that's what this signifies. A matrix in row echelon form is in reduced row echelon form if every column has a leading one, or every column that has a leading one has zeros in every position above and below its leading one. Which basically means there's ones in a diagonal like this, and there's no other entries. So what does this mean, really? This means that we've isolated all three variables. So we've got z equals something, or z equals whatever, y equals, and then x equals that. So we don't have to do any back substituting. We've just got it all right here, and that's what reduced row echelon form is. And then the little text note down here below the box, it says, it is worth noting that the row echelon form of a matrix is not unique. That is, two different sequences of elementary row operations may yield different row echelon forms. So what that means is kind of like how I was saying in systems of equations, how there was multiple ways to go about solving it, and you would end up with different equations, but as long as your math was right, the variables would come out to have the same value, you know? And so that's how you can get different row echelon form values or matrices. But when you solve for those variables, if your math is right, which it should be all the time, right? Because we're really good at math. When we solve for those variables are always going to have the same value, no matter how we solve it. And so that's why there's only one unique reduced row echelon form matrix, whether it's augmented or not, for any system of equations. So that's what being unique means. There's only one, like I said, there's only one value for x, one value for y, one value for z, whereas we have like an equation here, and we can have different equations that match the same system. So just a little overview over these two forms, just to get you all a little more comfortable with it.